Hi, my name is Ruben Villegas. I'm a computer science undergraduate student at the University of Central Florida. This summer, I participated in the 2013 Summer Research Opportunity Program at the University of Michigan, where I was given the opportunity to work on a machine learning project with Hongji Wang, Charlie Yang, Scott Reed, and under the supervision of Dr. Honglek Lee. The title of the project was Convolutional Neural Networks for Vehicle Detection. This is an ongoing project that I was included in. It takes advantage of 2D images and 3D point cloud information to perform the detections. My contribution mainly consisted of the refinement of the given detections by performing a search in the 3D space. I am going to talk about what the entire pipeline of the project consists of, followed by my contribution and results. I am going to start with a brief description of a convolutional neural network. A convolutional neural network is a system that takes in an input, in our case an image, which is convolved with a number of filters at every layer of the convolution phase. These convolutions produce pooled feature maps for every filter at each layer, which are hierarchical representations of the input data. Each feature map learns to describe different features of the given input that allows very good detections. After the convolution phase comes a fully connected neural network which will perform the final classification. In our case, it will tell us whether we have a car or not. As part of our dataset, we have point cloud information that corresponds to the images we're performing the detections on. Point clouds are 3D coordinates extracted from a particular area with the use of a 3D scanner. To take advantage of this 3D information, we compute spin image features on it. The spin image features are descriptors that we use to represent 3D data in more detail. These descriptors are extracted by estimating a normal line of a particular point with respect to its surrounding points, and thus this helps us estimate a plane that corresponds to that point. This is performed for every point of the object. This allows us to have a very good reconstruction of the 3D object with the use of the estimated planes. We use these descriptors to build a classifier for them. We use a histogram of oriented gradient descriptor for our images. This works by computing the gradient magnitude and orientation for each pixel within the patch we're analyzing. With this information, we split our patch into subpatches, and a histogram for each subpatch is generated based on the orientations. All the histograms for each subpatch are then combined into a long feature vector for the entire patch. We use these descriptors to build a second classifier. For the 3D search, we use a technique called hierarchical clustering to divide the point cloud into groups and subgroups of points. Here, I am using a 2D coordinate system to better explain how hierarchical clustering works. We first start with a bunch of points in space, then we compute the similarity between points using Euclidean distance and put them into the first hierarchy of groups. Some of the points may be by themselves because the distance is too great compared to the given cutoff point. After that, the points and groups are further clustered into the next hierarchy of groups. This happens until all the points are one big group, which will be the highest hierarchy. The different clusters are then used to see which gives the best detection scores, and then we move the detection box to the highest score location. Here is a visualization of one step of the process. As you can see here, the blue box, which is the original detection, was shifted to the left during the first performed search. Since the new bounding box is not resized to contain the high detection cluster only, it will contain new clusters, and this search is repeated within the new bounding box until no better clusters are found. Here are some results. In the picture on the left side, we can see how the car all the way to the right is localized better by the red box compared to the original blue box, even though the car is occluded in the 2D image. In the picture on the right, this also happens with the car located all the way to the left. Also, we can observe that one of the boxes that doesn't have any car inside did not move. We might be able to use this in our advantage by checking if the majority of the clusters pass a certain threshold to decide if we can eliminate this box. Before I end with the presentation, I would like to take a chance to thank Dr. Lee for giving me the privilege to work with him, and to thank Charlie, Hongji, and Scott for collaborating with me in this project. Thanks for watching.